Hello, welcome to Practical Electronics 9. Our topic is DIY PC Sound Card Oscilloscope. So what is a sound card? What is oscilloscope? A sound card is a dedicated ADC. ADC stands for analog to digital converter, and DAC stands for digital to analog converter. So a sound card is a dedicated ADC and DAC for audio frequencies. A sound card is a circuit board found in the motherboard of our personal computer that processes sound. It converts digital sound that is stored in the computer to analog that we hear on the speaker, and also it converts analog signal that we feed in through our microphone that will be converted to digital and stored in the computer. Then what is an oscilloscope? An oscilloscope is an electronic test instrument that graphically displays electrical signals as a plot of voltage versus time. It allows you to visualize the waveform of an electrical signal. So what I have here is PC Sound Card Oscilloscope. So what I'm having here, this is the device that I'm talking about, which I've already built. So you can see it. Now, the oscilloscope is a very useful piece of instrument. Now, if you look at it, the standard oscilloscope, the digital oscilloscope, that's our modern digital oscilloscopes we have in our electronics labs, physics labs. They are very expensive. So here we have a DIY, that's do-it-yourself PC Sound Card Oscilloscope. So what I'm having here, these are the outputs that will go to your computer through this audio jack connectors. See, so this end goes to the microphone input of your computer. Now every computer has an inbuilt sound card. The sound card has input and output, microphone inputs, and also headphone output. So this port here is where I feed my signal in through these connectors. So these are the two channels, the inputs, channel A and channel B. Then here is my ground. So what I'm having here is my input. I can feed in signal, either a sine wave or a square wave or a triangular wave. And then at this point, the output goes to the sound card on your computer. Your sound card could be something like this. If your computer on board sound card is faulty, this external, this USB sound card. So here we have as you can see it here, we have the microphone and the headphones ports. You can see. So so if you are taking into this, it goes to your computer. So your laptop or your desktop computer already have this inbuilt. You understand? You already have this inbuilt. So your computer already have this, so you don't need to construct this. So this is what we just need to build, and this is passive. It means there is no active component. You don't power this. Everything here is just passive. Then this, what we have here, they are the controls. So let's take a look at the circuit diagram here. So as you can see, these are the two channels, channel A and channel B input. Then these are ground. So you can see them, your channel A and channel B inputs, and then this one here is our ground. So here we have a fixed 100 kilo ohms resistor, and then we have a variable resistor, that is a potentiometer, 100 kilo ohms. Then here we have some signal diodes. Here we also have a fixed resistor. Then this is the output. You understand? Your right channel and your left channel, and then your ground. So that's what we have here. Your right channel, your left channel, and the ground. See, your right channel, your left channel, and then this outer is the ground that you see here. So this is the cycle. So there are two channels. So what we have here, one channel, then what we have this one, the other channel, the second channel, then this is the ground. So here we need to give some input resistance, like I used a 100 kilo ohms resistor. You can use something less than that or even higher than that, depending on the input voltage of the signals that you're going to measure. Then here we need to protect our computer sound card. You understand? So for example, now you connect 50 volts here. Without all this, you could damage your computer sound card. Even the motherboard of your computer, you could destroy it. So here we have, these are voltage clippers. So it will now allow the voltage, it will clip the voltage to 1.2 volts. So these are, you can see these diodes are arranged this way. AC signals, it will clip it. If the voltage goes higher than that, to clip it. So you see, so then I also have some output resistance here, like I use 1 kilo ohm resistor. So I repeat both for both channels, because we have two channels. So here, these are purposely for to control the amplitude. It's all like the way you control the volume on your audio amplifier. So it's very, very simple. This is just a passive. So it's very, very simple. So this is where you can feed your signal. For example, now you can feed a sine wave signal. You can even feed here a square wave signal. And then this is where they enter into your, because since your computer sound card is stereo, that's right and left channel, the microphone ports on our laptop and our desktop computers, they are stereo, they are two channel. So we are taking use of that. So the whole circuit, you can see it is passive. There is no active component like transistor or IC, anything, no. You understand? And this is working very well. So here we have the inputs, the amplitude control, that's the signal level. Then we have the clippers. This clips the voltage at 1.2 volts. It will not exceed that. So just to protect your computer. Then the output to your microphone. That's why when you are buying a computer, for example, you want to be using your computer for experimenting and for electronics and embedded systems practicals, make sure the computer that you are going to buy is having a microphone input separate and then an headphone output separate. You understand? So that you can use to do things like this. And if you look normally, the standard oscilloscope, they are very expensive. They are very expensive. So with this, if your signals that you are going to measure is below 20 kilohertz, you understand? So you can be able to use it. But if your signal that you're measuring goes far beyond it, that's where you need to get some digital oscilloscope. But with this, you spend less. For example, if you design inverter, like for me, I build inverters. So your oscillator of your inverters, you want to view the waveform. This goes a long way to help you, instead of saving big money, looking for big money to buy, large amount of money to buy an expensive oscilloscope. With this very simple setup you're seeing here, one good thing about this is that we have free softwares available on the internet. For example, this one I use, Visual Analyzer for Windows. You can just go and down. We have so many of them. Some are free, some are not free. So this particular one is free and it's very good. So you just install this on your computer. So the sound card processes the signals and then being captured by the software. So the software plots them on the screen. So let's see how the signal is captured. This is how the signal is captured. Number one, an analog signal enters the sound card's microphone or line-in jack. The sound card's internal ADC, that's the analog to digital converter. Now, when you take a microphone, you plug in into your mic input jack on your sound card, and you click on the record button of whatever software you are using for recording. As you are talking, your microphone converts sound energy into electrical energy. It goes through the cable to the ADC input on your sound card, and then the sound card converts this to digital format and then saves it in your computer. So the audio signal that you feed in is saved in digital form, so that later you can convert it back to analog, that's using the DAC. For example, you store music on your memory card. The music in your memory card is in digital format. Then you put the memory, you replay back the audio from the memory card, let's say in your MP3 player or even from your computer. The opposite now will be DAC, digital to analog. So it has to be reconverted again back to analog and then sent to the amplifier, and then you hear it. You understand? So the ADC samples the voltage of the signal at a fixed rate. Example for 44.1 or 48 kilohertz. These digital samples are sent to the PC via the audio or USB ports. Just like the one I have here is a USB. It's USB audio. In fact, you don't need this because every computer has an inbuilt sound card that you can use with this oscilloscope. But in case yours is having issue, you can just go get external sound card, but make sure the mic input should be stereo if you are buying anyone, because most of these external sound card, their microphone are mono, which you cannot use with this, because this PC oscilloscope here, this thing is having two channels. So make sure your sound card, your USB sound card that you're going to get, make sure it is stereo. So you take note of that. Then the software that we have on the computer now, the software interprets these samples, plots them as voltage versus time, and displays the waveform on your screen. So on our computer screen, we have something like this. This is time, while this is voltage. So you see, so you could be seeing something like this. Something like that on the screen. You could also see something like this. On your screen. Also, you could be seeing something like this, or different kind of waveforms. So with this device, it's you don't need to or worry yourself of getting an expensive oscilloscope. For example, if you design or you consult inverters, our inverter oscillator is, we use others at 50 hertz. So with this, I use this for calibrating the oscillator of my inverter to 50 hertz so that I can also see the waveform. The type of waveform our oscillator is generating. Is it square wave, or is it sine wave, or is it modified sine wave or modified square wave? Is it triangular wave? Whatever waveform that you want to view. For example, now you want to view PWM signals from your DC motor controller. You can use this. It does that very well. So just like I've stated here, the limits of this less than or equals to 20 kilohertz. You know, anything above 20 kilohertz, most of our computer sound card wouldn't be able to display that correctly on the scope. So so from experimenting, you know, from 20 kilohertz above, beyond the audio hearing range. So with this, so if your signals are within this limits, you can be able to go with this. So for a simple stuff, you don't need to bother yourself of going to get expensive oscilloscope. So with this, it's a starting point. Now with this, this also helps you to study waveform. Let's say you haven't used a standard lab oscilloscope before. From this, you'll be able to learn waveforms on how they appear on screen. So the oscilloscopes actually gives us a picture of how signals flow through these cables. Your voltmeter can measure the magnitude, the voltage. You can measure the current, but your voltmeter cannot display the graphical properties of the signals. So it is the oscilloscope that shows you the waveform of these electrical signals. So take a look at the diagram very well, very simple, so that you can make yours. Uh, so you can go out and make yours. Hello, this is my PC Sound Card Oscilloscope setup. Over here, this is my Arduino board, and this pin here is generating square waves. So to this LED you are seeing here, that's a PWM. So I can vary the PWM. As you can see, the LED coming to bright, dimming it. You can see it. So from here, I've taken the output to my sound card oscilloscope. So then this output here are connected to my computer's microphone input. So my oscilloscope is at the amplitude controls. So you can see the signal input. You can see. So let's go to the computer. So here I've installed a software called the Visual Analyzer 2020. So I have to open the software. So this is a open source software for people who design stuff like this. So this is the interface. So I'm going to resize the window so that it fits my desktops. So yeah, so what you have here, this is the oscilloscope interface. There is 2 channels. So now I'm going to turn it on by clicking on this button. So you can see the waveform they are seeing from Arduino board. So this is the frequency. So it's two channels. Let me separate the two channels. Over here I can the position I can switch it to whichever way I want it, so you see. Then the other one I can shift it up. So these two channels. So you can see the waveform. You can see the waveform here, and then the frequency. So let me put some input to the other pin. You can see the waveform on the second channel. So this is how the scope works. So you see, so with this now I can be able to take in signal from the circuit and then watch the waveform on the PC. So you see, so that's it. Now make sure you use this, connect this way. It's very, very important. Don't skip this. Try to protect your computer. You understand? To protect your computer. So we are going to end our today's lesson here. If you benefit from this, please like, share it, and also subscribe to my YouTube channel. Thank you.